In the previous lecture, we started the discussion on digital circuits that have feedback, or in other words, circuit which employ feedback to be able to store certain information. Now, store in what sense? What is the difference between combinational circuits and circuits that contain feedback? The difference is, in a combinational circuit, so long as the inputs remain unchanged, the output also remains unchanged. However, in circuits with feedback, there may be certain times when the output might change even when the inputs are unchanged, or conversely, the output might remain the same even when inputs are changed. So, in the previous lecture, we sort of started with this very basic butterfly structure of two NOT gates connected back to front, and we saw that how these 2 points essentially contain logic with opposing nature, that is, these 2 points are complements of each other. However, we later modified this into a circuit where we can have additional inputs also. So we decided to replace these NOT gates with NAND gates, and we say that okay, let us still try to have these 2 points such that they are complements of each other. So we said that there is one input over here, another input over here, and the same butterfly connection existing. So one thing to note was that although this circuit by itself looks similar to a combinational logic circuit, this feedback by means of this butterfly structure is present. And we have these two outputs, Q and Q bar. So we had essentially established what is the truth table for this kind of a circuit. We had said that for inputs A and B, let us try to predict, given that there is some output Q which is being fed back, Q and Q bar, notice that they are being fed back. So in some sense, Q cannot be called totally an output. It is in some sense an input also, because it is being fed back. So therefore, these are not strictly called outputs, these are called as state, or the state of the circuit. So if the circuit has some known values of Q and Q bar, which are expected to be complements of each other, if the circuit has some known values of Q and Q bar which are existing, let's say at some point of time, for different values of A and B, can we predict what will be the future value of Q? That is like saying Q plus, this is called as the next state. The value of Q, which we know, is called as the state or the present state. Whereas Q plus is the next state. Now notice that there is no difference between Q and Q plus. Q plus is not a different signal. Q plus is not a different output or a state value. Q plus is simply same as Q except at a later point in time. So we had essentially derived this table. So we had said, we had seen that 0 and 0 is essentially a forbidden case. Forbidden, why? Because we saw that that is the only unique case when Q and Q bar both become equal to 1. Here for 0 and 1, Q plus becomes 1, 1 and 0, Q plus becomes 0. And for 1 and 1, Q plus is the same as Q. So if the present state is 1, the next state will also be 1 if A and B are 1, 1. Whereas if A and B are 1, 1 and the present state of Q is 0, the next state of Q will also be 0. This is what it means. So this circuit is called as a latch. Now a latch is a circuit which can have both combinational properties as well as memory properties. If you can see row number 1 and 2, it is as if this latch is behaving just like a combinational circuit. However, when A and B becomes 1 and 1, the next state is nothing but the present state. So therefore, it is able to hold on to the old value of Q. So therefore, this is the memory state. This shows memory properties. So latch is a circuit which has properties of both combinational circuits as well as memory properties in its simplest definition. Now, what we are seeing is that depending on the values of A and B, this latch can act either as a combinational circuit or a circuit with some memory properties. So in some sense, A and B has the power to act as combinational inputs as well as inputs which can activate the memory property. So now the question is, can we initiate these properties, whether it is combinational properties, whether it is a memory property? Can we initiate these properties based on not just the values of A and B, but at certain periods of time, but the control is given to the user? The user will decide when to activate these changes in the latch. So let us see how we can do this. Let us see how we can do this by using the present latch structure but making a very slight modification in it, and that is what we call it as a gated latch. So we take the basic latch, and draw it the way it is, except now that over here we have an additional NAND gate at every input. And these two are our earlier inputs, and along with these we provide a common input that is called as enable. We are providing the signal called as enable. We are still calling these 2 points as Q and Q bar, which are the state variables. Now we have to name these as A and B. But rather than doing that, let me call this as S and R. Why did I change these names? We will know very soon. Now, having said this, let us see what happens to the circuit when enable becomes equal to 0. Now, when enable becomes equal to 0, these two NAND gates get an input of 0. So therefore, the values of S and R are totally ignored because enable is now 0. So therefore, the outputs of both NAND gates become 1. Now when this basic latch structure gets both inputs as 1 and 1, the next state is equal to the present state. So therefore, if En becomes equal to 0, let's call these points as A and B because that's what they were. Then A equals 1 and B equals 1, which means Q plus is equal to Q as per the old truth table of this basic latch structure. Now the fun comes if enable becomes equal to 1. When enable is equal to 0, the next state is always equal to the present state, and this is the case where S and R values are ignored. Alright? Well, when enable becomes equal to 1, let us then draw the truth table where the next state is a function of S and R. So when S and R are 0 and 0, again A and B become 1 and 1. So in this case, A equals B equals 1. So therefore, Q plus will be the same as Q. When S is 0, A becomes equal to 1. When S is 0, A becomes equal to 1. And when R is 1, in the second case, En is 1, 1 and 1 becomes 0. So in this case, A is 1, B is 0. So in that case, the next state will forcibly become 0. When S is 1 and R is 0, A is 0, B is 1. In that case, we get the next state Q plus forcibly equal to 1. Now when S and R are both 1, A and B become both 0. So therefore, Q and Q bar both become 1, which is nothing but that forbidden state. So what we see is that when En equal to 1, this whole structure is acting in a very similar way to the latch structure which we had seen. Of course, the order of the outputs has changed. The order of the values of the next state Q plus has changed. Earlier it was question mark 1, 0 and Q. Now it has become Q, 0, 1 question mark or forbidden. But all said and done, the operation of the basic latch structure using the basic butterfly structure that we had started with, that does not change. So effectively what we have done is that we have given a control element to the user, that is in the form of enable. So when enable becomes equal to 0, that means no matter what is the value of S and R, the next state will always be equal to the present state. But if enable becomes equal to 1, the normal structure or the normal latch operation can continue. That is of the basic feedback butterfly structure. So therefore, this enable input is also called as a latch enable. This enable signal or this enable input is called as a latch enable. So therefore, when En is equal to 1, we say that the latch has been enabled. When En becomes equal to 0, the latch is disabled. So when the latch is disabled, it essentially acts like a memory element. No matter how you change S and R, the next state stays equal to the present state. However, even when the latch is enabled, when S and R are 0, that property of the next state being equal to the present state, that still continues. Is that fine? Now let's come to why these are called as S and R. Initially, I had said that let us name these as S and R, and later we will see why they are named like that. When enable becomes equal to 1 and S is equal to 1, we see the next state is 1. Whereas when R is equal to 1, the next state is 0. So therefore, S is called as a set input and R is called as a reset input. Set means when the output or the state goes to 1. Reset means when the state, that is Q, goes to 0. So essentially, in computers, you have a reset button. When you press reset, the state values of most circuits in the computer become 0. That is why the name reset. And usually, the input variable set indicates that the state value should go to 1. So therefore, this entire structure is called as a gated SR latch. Now this was one of the earliest latches which was designed by digital engineers. And this sort of helped them to store the data as needed or override the data as needed. So essentially this is when this is called as data stored. When the next state is equal to the present state. Same over here. Data stored. These two conditions, when R is equal to 1 or S is equal to 1, we are forcibly writing a 0 or a 1 to the next state. So therefore, this is called as data write onto latch. So this is acting exactly like a read and write memory. What this means is we can use this as a memory element. When we want, we can store a 1, or we can provide a 1, we can provide a 0 as per our requirement, what we want to store. And when we can make S and R as 0, we can store whatever is the value that we have written into the latch. So truly, this is also called as a 1-bit memory cell. Because, or I should say 1-bit read-write. You can write to it, that is you can write data values of 0 and 1 onto the state variable, and you can also store that which can be read at any point of time. Read means access. That is like saying whenever you have a directory in your computer, if the directory is empty and you want to store a file in it, you send the file from somewhere into that directory. That is called as a write operation. After that, when you don't disturb the directory at all, you can access it anytime the computer is on and access the file that is inside the directory. So therefore, that is called as a read process. So just like that, what is happening over here is that this memory cell can be used to store data as well as provide new data to it. That storage process is called the memory property, and that stored value can be read or accessed at any point of time. We can also write some data into that latch or the memory cell by choosing proper values of S and R. We can even choose S and R for storage or reading. Now, having said this basic fundamental, let us look at the truth table of this gated SR latch in more detail. So let's see. Now what is happening is that Q, which looks like an output but is also being fed back, as I said, is not really called an output. It is called as a state variable. So therefore, the truth table of such circuits is not called a truth table, it is called as a state table. State table of SR latch, I will say the gated SR latch. So therefore, let us write this down in terms of the enable input. So when enable is 0, it does not matter what S and R is, Q plus is equal to Q. When enable is 1, we will consider the values of S and R. When S and R is 0, 0, Q plus is still equal to Q. So here R is 1, so Q plus will be 0. Here S is 1, so Q plus will be 1. And for 1, 1, this is a forbidden state. So therefore, what we are saying is that from the operational point of view, the very first row is not really very useful. So we can compress the state table and just simply consider the cases into when enable is equal to 1. That is when we are more concerned about the latch behavior, because that is when the latch is enabled. So we will see that Q plus can be expressed as functions of S and R given that enable is equal to 1. We are not going to be treating this enable as a separate input anymore. For the state table, of course it is a separate input, we cannot forget that, but for the state table purposes we will not consider this because En is always 1. So therefore, for these 4 conditions, we can write that Q plus is equal to Q, 0, 1 and forbidden. Now what we will do is to look at this state table more deeply. There is one thing which we still have to solve. That is the case of the forbidden state. Now suppose we say that as engineers we are careful. We say that we will never ever give 1 and 1 to S and R. So we will treat this as a can't happen scenario. Suppose we say that this cannot happen. So therefore, we really don't have to worry about the forbidden state coming. As long as we have been responsible engineers and ensure that these 2 inputs never get 1 at the same time. So therefore, we can treat this as a don't care. We can treat this forbidden as a don't care condition. So this state table, we can then represent in a more detailed fashion. So let us say the next state is a function of the present state also. So let's consider the present state as an input variable and try to establish the next state as a function of these 3. Before solving this state table, it may look as though Q and Q plus are different because Q plus is an output, Q is an input, but no. I have already mentioned that Q is an output which is fed back. So because it is fed back towards the input side, we cannot truly consider it as an output. It is a state. And Q plus are not different. All I am saying that if the present state is this and the values of S and R is so and so, what will be the next value of Q? So Q and Q plus once again are not different. They are the values of the same wire, same signal, but at different points in time. Now when S and R are 0 and 0, we know that Q plus will be equal to Q. So here for 0, 0, Q is 0, 1. So even Q plus will be 0, 1. Now, when S and R is 0, 1, no matter what the value of Q is, Q plus will be always 0, just like a combinational circuit. So therefore, for these two rows, the Q plus will be 0. For 1, 0, Q plus is 1. So for these two rows, Q plus will be 1 and 1. And over here, for 1, 1, since we are treating it as a can't happen scenario, we will simply consider these two as don't cares. So with this, we have written a longer truth table, which is called as the detailed state table. This is called as the compressed state table. This is called as the detailed state table of this gated SR latch. Now let us see what we have achieved. For this circuit with feedback, this gated SR latch, which acts like a 1-bit memory cell, we have seen that if the inputs S and R are known and the present state Q is also known, we can predict the next state value. Now, let us ask a converse question. Suppose we know what the present state is. That is, we know what the value of Q is. And there is some value in future that we want. That means we know what we want for Q plus. We know Q. But there is a Q plus which we expect in future. Suppose I want a 1 or a 0, I can expect that. So if I know what is my present state, and if I know what I would like to see as my future state, then can I make this happen? Can I make this happen by providing proper values to S and R? Yes, we can. So therefore, let us treat as though the present state and next state are inputs. And corresponding to these two, we will try to see what values of S and R make this possible. What values of S and R make the combination of the desired present state and next state possible? Suppose we write it this way. So when Q and Q plus are both 0, let us see when this happens over here. This is one condition, or this is one such scenario, and this is one such scenario. When Q and Q plus are both 0. So corresponding to these two rows, let us see what is the value of S and R. In one place it is 0, 0, one place it is 0, 1. So therefore, for both cases, S is 0. And the value of R in one case is 0, the other case is 1. So what we see is that the value of R does not really matter. So therefore, we will put R as don't care. Now when Q and Q plus is 0, 1, when Q and Q plus is 0, 1, that happens over here and here. So for these two, what we see is in one case S and R are 0 and 0. The other case, it is 1 and 0. So therefore, R has to be 0. R has to be 0. And in one case, S is 0. The other case, S is 1. So therefore, in this case, S does not matter. It is a don't care. Now for 1, 0. oops, I made a mistake. By mistake, I took this for 1 and 1. So therefore, for 1 and 1, that is when q and q plus are both 1 and 1, this is what will apply. So this will be x at 0. For 0 and 1, let us take 0 and 1. This is the only case when it happens. And for that, S and R are 1 and 0. For q and q plus as 1 and 0, this is the only case when it happens. So for here, q is 1, q plus is 0. So for that, S is 0, R is 1. Okay, so let's write this table in a little better way. So we had started the discussion on this table by assuming that we know the present state and the next state which we would like, and corresponding to that we would like to make that happen by having the proper values of S and R. So this is 0 and don't care. This is 1 and 0, 0 and 1, don't care, and 0. Now, this table looks very weird. We have outputs, or rather the state variables on the input side, which are very similar to outputs, and the inputs on the right hand side. This table is called as the excitation table. The excitation table of gated Sr latch. Now there are few things you to note. The first thing is excitation table cannot be represented as a circuit. Excitation table cannot be implemented or represented as a circuit because the input side variables are the present state and the next state. You cannot have access to present state and next state as two different signals. It's like saying that I have the future also known to me. No. The future also available to me? No. That is not possible. So this is simply a table for our own reference and analysis. This is a table just for our own reference and analysis. That is, if we know the present state, this is available, Q is available to us. Q plus is not available right now, it will be available later to us. Now Q plus will become a new value of Q. So if we know what the value of Q is and we would like a certain future value of Q, that is Q plus, based on what is the value of Q that we know, then what are the possible combinations of S and R that are required to make this desired future state possible? This is what the excitation table is all about. So therefore, this is the present state. This is available to us. This is the next state. This is expected, but not available with Q. This is the future value of Q. The other assumption is that En equal to 1 is implicit. The enable equal to 1, that is the latch has been enabled, that is implicit. And from this point onwards, whatever be our discussion on latches, we shall always assume gated latches. Alright, so this is how you can derive the excitation table of a gated SR latch. Now, the next question is, we have seen a lot about the basic latch structure, how we can modify that to have a gated latch. We made the gated SR latch or the gated set reset latch that we called it. Now, are there any other types of latches, the gated latches available for use? Yes, there is. There is one more latch that is available, and that is called as the D latch. Now, the D latch is a very simple modification of the gated SR latch. So, the gated SR latch looks like this. This is Q, this is Q bar. This is the way. This is the basic butterfly structure. Now, to make the gated SR latch, we add these NAND gates. There is a common input, that is the enable input, and then there are two more inputs. So far, this is exactly the same as that of a SR latch, a gated SR latch. However, we can very easily make a D latch from a gated SR latch, that is using this as a starting point. We will call this as D. SR latch has two inputs, S and R. D latch has one input, that is D. What you do, you take this, take its complement and feed it to the bottom input. This is called as a D latch. Once again, when enable is equal to 0, this behaves just like a gated SR latch. In that case, when enable is equal to 0, the value of D does not matter. These two values, again, let's call them as A and D. They get 1 and 1. So therefore, Q plus is equal to Q. Q plus is equal to Q. But when we enable this latch, we make En equal to 1. Then for D, we have to calculate what is the next future state. But we don't need to do that. Whatever is the value of D, the upper NAND gate gets the value of D and the lower NAND gate gets the value of D bar. So when D is 0 and 1, this behaves just like a combinational circuit. This behaves just like a combinational circuit where we essentially have these two cases of the gated SR latch, because now the inputs to S and R are complements of each other in the case of D. So what we see is that the D latch is just a subset of the gated SR latch. Why? Because it is essentially the same structure as the gated SR latch, but the inputs are complements to each other. Okay, so therefore whatever is the values of S and R in row number 1 and 2, that will be the value of Q plus, and that is 0 and 1. So you may ask, this looks just like a combinational circuit. Where is the memory? Well, in this case, the D latch achieves two useful properties. it now delegates the memory property purely to the condition when enable becomes equal to 0. So when enable becomes equal to 0, the memory property is satisfied. And when enable is equal to 1, this is the right process. So the enable is now used as a unique identifier. When enable is 0, the next state is the present state, which can be used to read this memory element. But when enable is equal to 1, you can write new values to this latch, and that value can be given through D. This is one advantage. The second advantage is that the forbidden condition from the gated SR latch, when S and R both become 1, that condition is removed. So here you don't have to worry about the forbidden state at all. Alright? So this is called as a D latch. Now let us see how this D latch works with the help of waveforms. How does this D latch work with the help of waveforms? Suppose D changes like this. I am drawing a unipolar signal. And so on. Now suppose the enable is initially 0. And so on. Now what will be the value of Q? Now notice again we are not showing what is Q plus. Q and Q plus are the same signal but at different points in time. So if you assume that initially the Q is 0 and the enable is 0. So far as enable is 0, the Q will continue to be its old value. But at this point of time, the enable becomes 1. So therefore, whatever is the value of D, that will be equal to the value of the output state. So therefore, here D is 1. So therefore, we will get 1. Until which point? Until this point. So over here, the enable is still high. So therefore, whatever is the value of D, that will be the value of Q as we have seen in the state table. So remember what the state table was we had derived in the previous page. Whatever is D, the same will be the next state. It's very easy to remember that also. Now here this will go to 0 and this will continue to go to 0 until this point. Now over here, once the enable becomes 0, it does not matter what the value of D is. So this continues to be 0, the old state. Once again here, the enable becomes 1. So therefore, this will follow the value of D. So here, the D will become 1 and will continue to be 1 until this point, when the enable again goes to 0. Now over here, when the enable becomes 0, the D continues to be 1, but here now once that the enable has become 0, it does not matter what the value of D is. Q will continue to be the old value of Q until the next time enable becomes 1. So therefore, what you see, just to have a notice, even here if D becomes 0, if D becomes 1 at this point, the output does not reflect that 1. It has to wait until this enable becomes 1. So therefore, this transition essentially gets delayed and comes over here. So therefore, the D in the D latch stands for delay. So there is some kind of a time delay, which is now sort of a consequence of the logic function rather than the delay of the individual gates. So therefore, if you want to generate a delay, you can use the D flip-flop, or the D latch. So now I mentioned a word called the flip-flop by mistake, and that is what we will discuss in the next class. Now the flip-flop is just one step ahead of the latch, but it is ahead of the latch in a small but a very significant way. And what that way is, we will see in the next lecture. So in this particular lecture, we delved into the analysis of the SR latch by making what is called as a gated SR latch to have better control by the user. So we derived what is the state table of the gated SR latch. We derived, using the state table, the extended state table, and from that we derived what is called as the excitation table. And from that we also modified the gated SR latch to make what is called as a D latch, and we also derived the state table for that. I leave it to you as an exercise to find out how you can derive the excitation table of a D latch in a manner that is very, very similar to what we did for the gated SR latch. And as promised, we shall start the discussion of flip-flops from the next lecture. Thank you.